These lights and the sound effects you can hear are being controlled by a simple scene-based engine that's running entirely on this ESP32 microcontroller. So right now I've got a stormy scene with randomly timed white lightning flashes and a rumbling thunder sound effect. But these could fade into an ominous red pulsating look with dramatic theme music, or transition again into a steady rain effect. And you can have as many of these scenes as you want. Each one defines an effect function that generates DMX values used to control the lighting fixtures, as well as an audio track which is being played alongside through these speakers. And you can either specify a duration that each scene lasts for and then automatically advances to the next in the sequence, which could be synchronized with the music track. Or you can manually trigger a transition to a new scene, and that trigger could come from a button input like this, or a sensor, or when a command is received over a network. And you can specify a duration of time that it takes to crossfade into the next scene, or you can just instantly cut to it. So you could use this as a simple show control where you have a list of scenes that you want to step through on a linear timeline like a queue list, triggered manually by an operator or by some event. Or you can just have it automatically run in a kind of attract mode where it cycles through a set of predefined scenes in a loop. Or if you're running an interactive attraction like an escape room or a haunted house, you might like to trigger an effect or change the mood of the scene in response to a player action. Now, obviously this is not as powerful as a dedicated show control software, but it is self-contained, it doesn't require a lighting operator or expensive hardware, and you can buy all of the components which I'm using here for about $15. And even using it to control basic LED lighting fixtures like these that you can buy on Amazon, it can dramatically enhance the theatricality and the immersion of your experience. And in the rest of this video, I'm going to show you how to make this yourself. Now let me show you the hardware I'm using in more detail. So I've got an ESP32 board which I've just mounted onto a breakout shield for convenience. This doesn't add any functionality, it just exposes the pins in strips next to their own ground and VCC lines, which makes it much easier when you're trying to connect other modules. Now you could use an Arduino if you wanted to, but the ESP32 is more capable. It's got more memory to store scene information and a faster processor to be able to calculate effects. But I'm not using any specific hardware features on the ESP32 that aren't also available on any other microcontroller. Now this is an RS485 Transceiver module, and RS485 is the physical networking infrastructure layer on which the DMX protocol is based. So on this side of the module, I've connected GPIO pins to the transmit and receive lines, as well as to ground and to VCC. Now, because I'm using an ESP32 that runs at 3.3 volt logic, I'm supplying 3.3 volts on the VCC line. But if you're using a 5 volt microcontroller, like an Arduino, this will run with 5 volt on VCC just as well. And what this does is it converts the data on the transmit and receive lines into a differential pair of signal lines called A and B, as well as ground. And the point of a differential signal is that A and B actually carry exactly the same information, except that one is an inverted copy of the other. So when A goes high, B goes low, and vice versa. And DMX data is encoded as the difference in the voltage between those two lines. Now that's a lot more robust than something like SPI or I2C that just measures high or low values on a single line. It's less susceptible to noise, and it means that data can be carried along cables a lot greater distance. That's why this is the standard used in theatre and stage lighting control systems. Now, the DMX standard itself specifies that that data should be carried along connections made using a 5-pin XLR connector like this. But because you don't actually need 5 connections, it's common for cheap DMX lighting fixtures to only use 3-pin XLR connectors like this one instead. So that's what I've wired onto the end of the RS485 module here. So I've got the ground pin going to pin 1, I've got A going to pin 2 and B going to pin 3. And then I can take my standard 3-pin XLR cable and I can just plug that into the module like that. Then I can take the other end of that cable and connect it to my lighting fixtures. Now it is worth mentioning at this point, so according to the RS485 standard, A should be the inverted signal and B is the non-inverted signal. But if you look at this RS485 module, it actually says A positive and B negative. And I looked at a handful of other modules as well, and it does seem there's a little bit of discrepancy or confusion as to exactly how these pins are labelled and used. So if you do connect a cable like this and you find it doesn't work with your lighting fixtures or they're jittering a bit, it might be worth trying to swap your B and A connections over. There are also some sort of DMX fixtures that don't use DMX cable at all. So I've got one here which actually has, this is a DMX interface, it uses an Ethernet RJ45 connection instead. You'll get some that have screw terminals, just like the module here, so just labelled A and B, in which case you connect A to A and B to B. That's it for the lighting. Now let's take a look at the audio output. So for the audio output, I'm using one of these DY Player MP3 modules. So these are great audio modules which I've used in several of my projects in the past. They come in a couple of different varieties. Some store the audio data on an onboard EEPROM memory chip, which is convenient, but it does mean that you're limited in the storage space available. So normally you get at most about 8 megabytes of storage on one of these, which is fine if you're mostly playing sound effects or short music clips. But if you want a playlist of full songs, you might prefer to get one of the varieties with an SD card slot instead. Whichever one you choose, you use exactly the same way to access them, the same programming interface and the same wiring. So I've got a serial connection here which has transmit and receive, and again VCC and ground lines, and then you can issue signals from the ESP32 to tell the board to start or stop playback, to choose a particular index number of a track you want to play, and to adjust the volume and things like that. Now another different sort of variety of boards you can get differ in the power of the onboard amplifier. So this board here I've got, this is a DY-SV5W, and this only has a 5-watt amplifier. Now more commonly in my projects I use the HV models, which are the next model up, and they have a 20-watt amplifier chip on board, and that's plenty sufficient for a lot of the prop-based audio which I normally make. But on this occasion it's still not really sufficient for a stage sound effect that you really want to fill a room. I'm going to need to use an external amplifier for that anyway, in which case it doesn't really matter what the power of the onboard amplifier is going to be, because I'm not going to be using that. Instead, what I'm going to do is to take a 3.5mm cable and plug it into the audio line output here, and then I'm going to take that to an external amplifier, and that's what's going to power the speakers. Now in terms of the control input, the button I'm using, well, this is just a simple arcade push button, but you could also add any other inputs or sensors you wanted to any of these available GPIO pins still. So you could have a PIR sensor, like a burglar alarm that detected when someone came close, or a pressure mat on the floor, for example. And because this is all running on an ESP32, you can also use any of the other built-in connectivity as well. So you could have a Bluetooth controller, or connect via Wi-Fi, or use an RF remote controller to control the sequencing playback. And here's a fritzing illustration of that circuit. So this is exactly the same wiring as I just demonstrated. It's just a little bit easier to make out the detail in this diagram of exactly which pins I've assigned to which function. So as I mentioned, both the MP3 player module and the RS485 module use a UART serial interface. So they both need a pair of wires, a transmit pin from the ESP32, which goes to the receive port of the module, and then the transmit pin from the module goes back to a receive pin back at the controller. And generally speaking, you can assign most any GPIO pin you want for both the transmit and receive function. If you're using an ESP32 like I am, it actually has a number of hardware serial ports available, but you can map those hardware interfaces to pretty much any GPIO pin you want. If you're using an Arduino instead, well, that's only got a single hardware UART interface, but you can use a software serial emulation, and I'll show you how to set up both of those in the code in a minute. There's also just a couple of other special pins that you need to watch out for. There's actually a very useful reference guide on this web page that I often end up referring to. So this will give you a list of all of the pins on the ESP32, and if there's any special notes about which you can use. So for example, it mentions here that pin 12 is one of the bootstrapping pins, and although it says it's okay to use it as an output, you need to be careful of using it as an input, because if anything pulls that pin high, the ESP32 will fail to boot. Now, I'm using pin 12 here, but I'm using it as the transmit line that sends data to the MP3 player, and I'm using 13 as the receive line. Now that's okay because the ESP32 is driving the output of 12 high or low, so it'll be fine. If you were to have assigned these pins the other way around, so if you'd had pin 12 as the receive and pin 13 as the transmit here, there's a chance that the audio player here would drive that pin high and the ESP32 wouldn't boot. So you just need to be a little bit careful of which pins to use, but generally speaking, you can assign them to whatever you want. The RS485 transmitter here, well, I've got that assigned to pins 27 and 14. There's nothing special about those. And I mentioned the wiring to the DMX plug, which I've got here. So pin 1 should be ground, pin 2 is negative, and pin 3 positive. But you need to be a little bit careful at looking at your board as to exactly how those are labelled, because there's not complete consistency in how that's applied. The button, which I've got up here, I'm going to use the internal pull-ups to pull up pin 15, and then when that's pressed, it's going to form a connection through to ground that will pull pin 15 low, so I know when that button has been pressed. And now we get onto the code that's running on the ESP32. And this is quite a substantial code listing for this project. I'm not going to be able to step through every single line here, but in fact a lot of it I included almost as a proof of concept, just to try and demonstrate some of the features that you could implement. So in practice you're probably not going to want to use all of this anyway. But I will just go through the structure which I used to approach this and an explanation of some of the design choices which I sort of made on the way. So I'm making use of the ESP DMX library, which you can get from here. This is going to take care of sending out the packets of DMX data using the right timing protocols and things like that. Again, if you're using an Arduino, there is a different DMX library that I think is called Simple DMX instead, but it basically handles exactly the same functionality. If you want to use a software serial interface for one of those UART connections, you can include that in the library here. You don't have to if you're using an ESP32, because you can actually exclusively use the hardware UART interfaces, but I'll show you how to do it in the code here. This is a library that contains the commands to control the MP3 player, the volume, the start and the stop, and the choosing a particular track to play. I'm including a math library, and I'm doing that because I want to have the ability to have pulsating lighting effects or other animations that are based on trigonometric sine functions and things like that. So I'm including the math library here. And this is just a utility library which I've used quite a few times. It's a really nice library that can handle button inputs, so it does the automatic debouncing, but it will also let you recognize things like double presses, long presses, things like that. So that's just a convenient way of reading that button input from the Q button. I define the pin which I've attached the button to, which I've just shown you in the wiring diagram. And these are the values for the RS485 module. I'm using a single port, and these are the pins which I've just given to the MP3 player. Now I'm going to set up a software serial interface on those pins, and I'm going to create an instance of the DY player class that is going to use that software serial interface. Now, it's possible that you want to include lighting effects without an associated sound file to play with them. Now, obviously, one way you could do that is to include a blank MP3 recording as part of your audio data, but I've also written into the code the option to just specify that there is no audio with this particular scene, and if that index of 0 is read later on by the playback engine, it will just simply not play any audio at all. I define a default volume. I think the values for volume can go between 0 and 31 are valid values. I've just assigned a sort of a mid-range value here, 20, and we're going to be handling sort of fades in and out based from that baseline later. So now we get on to how the lighting effects are handled, and I've defined a couple of different structs at the top here. So first of all, just an RGB value that's going to carry around 8-bit integers for red, green and blue values. Now obviously not every DMX fixture is an RGB fixture. You can get all sorts of things. You can get movers that have X and Y axes, you can have strobe effects, you can have fog machines that are all fired from different DMX channel values. It doesn't have to be RGB, but for the purposes of this demonstration, I'm simplifying things by just saying, okay, this is the scene color that we want to do. We'll represent that as an RGB value, and then we'll convert that into the appropriate DMX channels, depending on which fixtures you've got attached a bit later on. Now, an effect, that is the thing which actually creates the lighting animation, and the main function within the effect is this render function that returns an RGB value. Well, we've just defined RGB up here, and it returns an RGB value based on the current timestamp. So for any kind of animation, if you want to have like a sunrise, if you want to have rainfall or a pulsating thing, I'm going to pass in an unsigned long time value to the render function here, and that's going to spit back out the red, green and blue values that this effect calculates to be at that point in time. It's also got a reset function. For a lot of the effects, this doesn't really do anything, to be honest. It was mainly used for the lightning effect function. Now the lightning has a randomly timed interval in between each lightning flash, but when I first activate the scene, I want to make sure it starts with a lightning flash. So I reset it when that scene ends, or before the next time you load the scene again. I want it to reset from the beginning and ensure that the very first lightning flash occurs at the start of the animation, and then from then on they can be kind of randomly distributed. So reset basically reinitializes some of the internal timing values and the state of any kind of animation that you might want to kind of reset from the beginning each time you play it, and that's just the destructor function there. So effect is my most generic kind of class of effects, and then I've got a couple of specific sort of effects which derive from that. So I've got the simplest one, which is a solid effect. So a solid effect, you can see its render function here. Whatever the time is, it doesn't actually make use of the timestamp at all. It just simply returns the color that it was told to when it was constructed. So a solid effect just returns cyan or magenta or an R value of 121 and a green value of 67 or whatever. Then we've got a pulsing effect. Well, this is a little bit more complex because in this one we have a time period, And within that time period, what we do is we calculate a smooth sine wave curve based on the specified period, so the wavelength basically, or the frequency rather, of this sine wave you want to occur. I calculate that, and then I calculate the red, green and blue values as a multiple of the brightness of the wave function at this point. So all this means basically is if I say I want a pulsing red effect, for example, I construct an instance of this structure and I pass in the desired RGB value, but then I scale the supplied RGB input values based on the value of a sine curve that oscillates with the specified period. So here I've got a 2 second, this is measured in milliseconds, so every 2 seconds I have a curve that goes from full brightness down to 0 brightness and up again. So this is how you create any pulsing thing. And if you want a pulsing green light or a pulsing blue light or whatever, you can reuse this same structure and just create different instances of it with different RGB output values. So that's a different sort of effect. Then I've got my storm effect. Well, this is what I use for the lightning, although you could also reuse this same base here. Instead of calling it storm effect, I probably should have called it something like random blinking effect or something like that, because maybe if you wanted to have electrical sparks, let's say, or any other kind of slightly noisy, randomly distributed thing, you could use this same base class here as well. So what happens is it has a number of short flashes quickly in succession, somewhere between 2 and 5, and this is what I was talking about, this reset function that that initializes each time the scene resets. And when you call the render function to generate the RGB values that this storm effect should have at a particular point in time, it works out if we're about to start a burst of flashes, and if so, it does them very quickly with a very short duration of flashes, so only 20,000th of a second or 50,000th of a second, somewhere between those two values, and then we just count that many flashes with that interval. If we are not within a burst of flashes, we put a longer duration break before the next burst happens, so somewhere between 2 and 4 seconds, and then we start again with a new round of flashes. So we have somewhere between 2 and 5 flashes, very, very close together, then we wait for somewhere between 2 and 4 seconds, and then we have another burst of flashes. So this is my storm effect, and this is just a demonstration of how you can use different kinds of animation functions to create different sorts of phenomena, basically. I've got a rain effect. You'll get the idea by now. I mean, to be honest, these functions were kind of slightly arbitrarily written just to demonstrate different sorts of techniques you can use. So the idea with this is we've got some drops that each have an independent speed and intensity, and each contribute to the overall RGB value that the light output puts out. So I'm not actually rendering the raindrops independently, but you can imagine them as contributing to the overall kind of color wash that's happening, and they kind of build up these layered waves of rain, kind of that feels a bit like, you know, when you look out the window in the middle of a rainstorm, you see these sheets of rain coming down. That's what this is meant to simulate. And I often I have a random chance of having a significantly whiter wave as well, which you can imagine possibly it's distant lighting or just light being caught in the raindrops as they fall down. I've got a sunrise effect. So this is another way of using a mathematical function to create a kind of an animated lighting effect. With this one, what I've done is defined a number of keyframes, essentially. So I defined a sunrise as starting off at black, so that's RGB 000. And then we just have red, 80, and then red with a little bit of yellow coming through, or a little bit of green rather. So we go ready orange, then orange, and warm yellow, then warm white. So these, you can imagine these as keyframes within an animation that shows the color gradient, the palette of a sunrise. And what we do is when we pass in the now value, so the time at which we want to calculate the RGB value for this animation sequence, we normalize that. So we work out how long is it now since this animation started, and then we divide that by the duration, how long we want the animation to last for. So that gives us a value somewhere between 0 and 1 of how far through these sequence of frames we are. And then we use lerp, so a linear interpolation, between the corresponding keyframes. So if we're somewhere in the first fifth of the animation cycle, we interpolate between this value and this value. If we are in the second fifth, we interpolate between this one and this one, and then we interpolate between this one and this one. So this interpolation function, you can think that this is like a gradual blending basically. And all this function says to do is as the time through the animation progresses, choose the relevant interval between two adjacent keyframes and blend between them based on the proportion by which time has advanced between them. And what you end up with is this lovely kind of smooth changing gradient. In this case, the gradient of a sunrise, but you could use this for any, you could use this as a sunset just as easily, or in fact for any kind of gradual darkening between a gradient of defined colors. I've got a forest effect, and by now I think you're probably getting the idea. So you don't need to take too much attention because these are literally just random examples I chose of different kinds of environments and scenes and color palettes that could demonstrate different environmental functions with lights. And what you do is, so all of those structures there are examples, and then you actually instantiate particular versions of those that you want to use in your cue sequence. So for this cue sequence, I want to have a rain effect, a storm effect, I want my sunrise and forest. And then I've got two examples of pulsing effect, one which is using a red, so that's RGB 255000, and with a 2.5 second periodicity. And then I've got a slow pulsing green instead, where I've defined a green value here. And I've got a load of solid color values here as well. So you can add as many of these as you want. You can create new sorts of effects if you want. You can create existing effects but pass in different values, you know, to get all of the different scenes that you want to use in your sequence. And then we get onto the scene itself. So we've only been looking at the lighting so far, but each of the scenes actually consist of a couple of different factors in as well as just the function that generates the DMX value. So that's the effect. We also have the index of the audio track that we want to play from the MP3 player, and whether we want to play that as a one-shot audio, so just fire it off once and then not again, or whether we want to have a looping audio that will repeat for as long as the scene is running for. We specify how long the scene lasts, and that's particularly useful if we've set auto scene advance mode, so when the scene has been playing for a minute and a half or 40 seconds or however long it is, automatically advance to the next scene. That's based on this value here. And we can also define a fade duration. So rather than just cut into the next scene, each scene can define how long it takes to adjust the RGB values from the previous scene into the current one. And that's also used to fade the audio. Now, the DMX values, the lighting values, they can achieve a crossfade between the old value and the new value. The MP3 module I'm using can't strictly do crossfading because it can only play a single MP3 file at once. So instead, for the fade of the audio, what I do is I fade the previous audio out to 0 and then fade in the new audio from 0 back up to that default volume we defined at the code. So it's not strictly speaking a crossfade, it's a fade out and then a fade in, but when accompanying the lights, it's actually pretty effective and pretty covers up what's going on. This indeed is the transition function that transitions between scenes. So this just, again, like the interpolation I showed above, this just returns how far through a transition we are and returns the proportion between them there. That's used for blending later on. And we've just got an active property to say whether the scene is currently active or not. Now this is where we actually define the sequence that we're going to use this time around. So all the code up to now, these are kind of things you can include in your scene, in your sequence if you want. This is the actual sequence that we're going to run in the code. So I'm going to run the storm scene. I'm going to play the first audio track. I'm going to play it once only. This scene is going to last for 60 seconds and it's going to cut instantly to it with no fader time at all. Then we're going to transition to the pulsing red scene. This is going to play the second audio track and it's going to repeat that same track for as long as the scene lasts. The scene is going to last for 60 seconds and it's going to take 2 seconds to transition into this scene from the preceding one. So the fade time defines the fade in time for this scene from the previous one. It's not the fade out, it's fade in. Then I have my rain effect, which is the third audio track. It repeats, it's 6 seconds long and it takes a second to fade in. And in fact, if you want at this point, you can rewind the video and go back to watch the demo at the start again and you'll see that these are the exact set of scenes that I go through. You'll see I've got some no audio at the end as well and things like that. But this is how you define them in your sequence. And we'll define a constant of the total number of scenes, which we'll use just to wrap around when we get to the end. Then we get onto a couple of global values that are used to control the behavior of the sequence as it's going. So what scene are we currently playing? What's the index of the scene? When did we start playing this scene? This is based on the millis timestamp of when the scene was started. And we're going to use this to know when it's time to change off the scene, when the duration has elapsed. Auto advance, so as I mentioned, if you want, you can make a scene automatically go on to the next one when its duration has expired. If not, it will just stay on the current scene until manually advanced using the button input or some other cue that you've defined. We'll keep track of which effect we're playing, which audio we're playing, what the volume is, all things like that. I've just got a debug function here that will print out to the serial monitor at the bottom while this is playing which scene we're currently playing, what audio track is playing and things like that, and it's quite useful to use that when debugging just to show what's currently going on. I've got a couple of helpers functions here. So this is to handle the crossfading between two different RGB values for the DMX, and then this function here actually assigns the output RGB. So we've got the effect of the scene that's in progress. That has the render function that outputs an RGB value. And if we're currently transitioning between the scenes, we also have the render function of the scene we're transitioning to that gives an RGB value. And then we blend those two outputs together to give us the current transition value. And then we need to assign that to the correct DMX channel. Now, in the video I'm using here, I'm using two different sorts of lighting fixtures. The par cans on either side, they are using a very simple 3-channel DMX mode, where channel 1 is R, channel 2 is G, and channel 3 is B. The wash light, which is in the middle of the T-bar, that uses a slightly different structure. So for that one, the first channel is actually a master dimming channel, and then the RGB values come after that. And of course, every lighting fixture might have a different set of channels that you have to pass data into. So you might need to, well, you will need to adjust this function based on the exact DMX lighting fixtures you use, unless you happen to be using exactly the same as mine, in which case you can use this as it is. And what this is doing is it's saying, okay, this is the desired RGB value that we calculated based on all our effects and transitions and animations, all the rest of it. Now we need to assign it to the correct channels in the DMX packet that we're going to send out. So my par cans at the end, those are assigned 3 DMX channels starting from channel 1, and then my fixture in the middle, that listens to 4 channels starting at DMX channel 4, and the first one I've hard coded to always be 255, and I just fade it in and out using the values there. And again, you can use up to 512 channels of DMX data here. So if you've got lots of different fixtures, if you've got several fixtures that you want to behave the same, that's fine, they can share the same channels of data. If you've got ones that want to behave differently, and you can send, this doesn't have to be RGB data, you can send axis data to make a spotlight move and follow a target. You can pre-program animations on a laser or anything like that. But this is the function that translates basically the calculated value from the code into the DMX channel data. And then this function is part of the ESP-DMX library that then actually writes that DMX value out to the fixtures. Then we go on to the scene control. So this is the sort of the main function that actually plays one of the scenes in the show sequence at the top, but it doesn't actually do a whole lot, to be honest. All it does essentially is call into existing functions I've shown you. So we record what the current time is, because we're going to be using that a lot when we pass it to all the functions later on. We decide whether the scene we're transitioning to has a fade value assigned to it, and if it is, and we are currently playing an existing scene, then we need to do a fade between them. We assign all the values of the scene we're transitioning to, and if we are fading into the new scene, then we set some transition values. Otherwise, we simply cut directly into the new scene. And we do the same logic again with the audio as well. If there is no audio in the new scene to fade into, we stop the player. Otherwise, if there is audio that we're going to play into, we're going to fade out the current one and fade in the later one, which we'll do in a moment. We'll reset the old scene so it's ready to go next time, and then we'll just say that it's loaded. Here we've just got a helper function to go on to the next scene, and that increases the scene index by 1 and then starts it, and we call this function when the button is pressed on here. So every time the button is pressed, this is my go next cue button, my lighting cue button, and all it does is advances to the next scene. Here we've got the setup function. So everything up to now hasn't actually happened yet because we need to get to setup, which is obviously called when the program first starts. We just output a little bit of information, we configure the inputs, we start the DMX interface here. This is all kind of boilerplate code that comes from the ESP-DMX library, by the way, so you don't need to worry too much about this. This is the code to initialize the MP3 player module on the assigned pins with the correct sort of protocol. And we begin by starting the very first scene, so scene index 0. This is the update audio helper I was describing. So if there is no audio in the following track, then we just fade out to silence. Otherwise, we can't strictly do a crossfade in that we can't bring the old track down and the new track up at the same time. But what we can do is in the first half of the transition, we fade out the old track, and then we very quickly swap the new track in, but at 0 volume, and then we fade it up again between 0.5 and 1 of the way through. So that's just what this function here does. If we're in the first half, we're fading out. Else we do the switch to the new track, and this is just a little flag just to let us know when that new file has been loaded, and then we fade it up to the default volume again. For the lights function, again, really very similar. This is just about applying the transitions between the old and the new values and sending that out using the help functions, which I've already shown you about assigning the DMX values from the RGB and sending it out to the DMX. And then we get onto the loop function. Now the loop function's pretty short because basically all it does is call the functions I've already demonstrated above. There's just one more thing which I never actually demonstrated, but just so you know how you could do it. So I'm listening for serial input. So if you were to type a value on the serial monitor at the bottom here, what you could do if you wanted to is you could press the letter R on your keyboard attached to the ESP32, and that would restart the sequence from scene 0. Otherwise, if you typed a number between 0 and 9, what it would do is it would start the scene with that index. Or if you typed the character N, it would go on to the next scene. So that's the same as pressing the button input. So I never actually demonstrated this, but this is just an example of if you wanted to make a more complex system that wasn't a linear sequence of cues, but actually jumped to an arbitrary cue, you know, on some kind of notification message or whatever. This is how you could implement that, and I've just done that via a keyboard input here. Other than that, on every iteration of loop, if the auto advanced mode is turned on, and the difference between the current time and the time when the scene currently started is greater than its specified duration, then we go on to the next scene. Otherwise, all we do is we call on each iteration the update lights value to work out what the light should be doing, the update audio to work out what the audio should be doing, and we just listen for the button input on a loop. And that is it. So that just about brings me to the end of this video. I hope you found it useful or informative or inspirational, and that you can go on to use a system like this in your own escape rooms or other experiences that you make. As always, I will upload the code which I demonstrated running on the ESP32 over onto my Patreon account, as well as more details about all of the individual fixtures and hardware I'm using. So if you would like to download those, please do head over there and check it out. I want to take this opportunity to thank my Patreon supporters for their ongoing support so much. I really do value your generosity and your support that enables me to create these videos each month, so thank you. I also have a Discord server available. I'll put a link to that in the description below, where you can discuss this project or any of the other projects that I've shown in this channel and speak to other people who are making really cool, playful technology experiences all around the world. And you can also get advice and support from me and from other people. There's a Patreon only channel there as well that you can get support in. So do please head over there if you'd like to know more. Other than that, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.